Hello. I welcome you all to this another interesting screencast. And the problem reads: allocate the centroid x bar of the area and y bar of the same area. All right. So this time around, we are dealing with two centroids in the x direction and in the y direction. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We are dealing with centroid. What is centroid? Okay, centroid is nothing but a geometric, you can call it as a geometric center, right? Okay, yes. So you can have what is called a centroid of a line. You can have what is called a centroid of an area, like in our case. You can have what is called centroid of a volume, right? And if density rho is uniform in a given material, okay, then centroid coincides centroid coincides with the center of mass. And if the gravitational field, the gravitational field is uniform, if the gravitational field is uniform, then centroid coincides with the center of gravity, right? Great. So this is, I guess, enough. Let's solve this particular problem. So we want to find the x bar and the y bar. And let's look at this particular line that defines the area just below. That is from A to B. So if we were to write this as y equal to c squared divided by x, when you look at this equation, what does it remind you of? As x approaches 0, because x cannot be equal to 0, right? Right? We agree, right? X cannot be equal to 0. But we know as x approaches 0, what becomes of y? Y keeps on doing what? Increasing. So what is this behavior called? This behavior is called asymptotic behavior. This is where this line, it will keep on increasing, but it will never touch the y-axis. To keep on going up like so, okay? And it's the same thing with if we made x subject of the formula, okay? Y can never be equal to 0, and therefore as y approaches 0, we have also the same behavior this side, right? Asymptotic behavior, right? It will never touch the x-axis. So we have this asymptotic behavior on both ends, right? It will just be so close, okay, but it will never touch x, okay? On either end, as x approaches 0 in this particular first case, y increases, like I don't know. And also in the second case, this one here, as y approaches 0, x also does what? Explodes, okay? And we know to say this kind of behavior is called asymptotic behavior. All right. Great. So, and in this particular problem, we have only been given the distances, if you would like, or the points, or the integration constants, because we need to use this in the x-axis. We've not been given in the y-axis. Why? I mean, this is how the problem is. There's really no reason. If you wanted to, we could have had integration constants also in the y. We can cut this anywhere we want. We can cut it there, okay, and there, okay, and only consider this portion, right? We can cut anything we want, right? So there's no specific reason why we don't have integration constants in the y direction, only in the x. This is just how the problem itself was tailored, right? Great. So if that is the case, we are only limited to integrate with respect to what? Dx. Dx. Because we don't have any integration constants along the y-axis. And therefore, in this particular case, we're only going to have one strip in just one direction. There is nothing like choosing strips in either this case or the other case. Here it is just one. Just one. We just have to do with what we have. Sometimes life is like that, right? You only have one option. It's do or die, right? Okay, there we go. This is our dx. And then we know that this one here is going to be our y. And then the centroid position of this particular strip in the x direction, x curled, is equal to x. And then the centroid position in the y position is going to be equal to that point there, right? What is that point there? This centroid position is y bar is equal to y divided by what? By 2. Great stuff. By 2, like so. Okay, have we defined everything? Yes, we have. What is remaining? What is remaining? Sorry. This one here is from here, from here, okay, from there, like so, okay. Sorry about that. We are starting from, I thought, no, I was thinking this is my y-axis there. Okay, there's a gap in between. So we are starting from this point here, okay. This is the centroid x curled is equal to x from this, okay. All right. So I think what else? Let's define our dA. Our dA is going to be equal to, vertical height is y, and then the thickness or horizontal length is dx. All right. And then we know that this function, we can write it in terms of y as y equal to c squared divided by x. Is that fine? Yes, it is. Great. So we know that we want to find x bar quickly. So x bar is going to be equal to integral of x scaled dA. This x scaled is the centroid position of that small strip, all right, divided by the total area, okay. And then our x bar therefore is going to be equal to what is it? Integral, okay, integral from a to b, and our x scaled is just x. Yes, it is going to be x. And then dA, what is our dA? What is our dA? We said it is y dx divided by from a to b, and then just y dx. All right, let's replace this y. Using this y, we need to replace this we replace it there. Okay, when we do so, then we are going to have something like this. We are going to have something like this. From A to B, x, and then replace this y. What do we have? That's c squared. X, we can write x like so, minus 1, right? You can bring it up, right? We know about this, right? Great. We know about this. If you want to, you can leave it. If you don't mind, you can also leave it like that. If you don't like, just leave it. It's fine. We can leave it like that. And then dx, right? Divided by integral a to b. And then we have y c squared divided by x dx. Right. We can factor out the constants. We can factor out the constants, right? And then we do the integration. So this y and x cancels, all right? And then if we are to do the integration there, we only have a constant there. Therefore, integrating that, we have a c squared x, okay? Integrating from, the integration constants being from a to b divided by, what is the integral of 1 over x? We know that. This is something we know already, just like we know the integral of sine x or cos x. So we know that this one is equal to ln what? Ln x. Okay. This we know it. I know you know that. If you don't, then I've reminded you. Then of course, we know that we can factor out the others. So x bar therefore is going to be equal to, we have cx like so, and then we have a b minus a, right? And then c squared. This is c squared, not c2. C squared. And then down there we have ln b minus ln a. And then this and this goes. Then finally we are going to have x bar is equal to b minus a, not so, b minus a divided by ln b natural log, right? Remember, minus ln a. Okay, I think this is about it. This is the final solution for x bar, right? Yes, I don't think I've made any error. If I have, please remind me. But this is the final problem. The final solution for x bar. Right. Right. So now let's move on to y bar. Let's find what y bar is. So y bar is equal to integral of y cubed dA divided by integral of just dA. We've already found this total area integral of dA. We found this, and it's equal to c squared, right? Ln b minus ln a. All right. So this is our total area. We found this already. So we're just concentrating with the top. Okay, so our top, which is y cubed, I'll just do the top and then I'll divide them later on. This is going to be equal to, integrating from a to b, we have y cubed, which is equal to just y over 2, and then the a, we say this y dx. Okay, and this is equal to integral from a to b, y squared divided by, we can factor out the 2 outside, dx, which is eventually equal to 1 over 2 integral from a to b. We can replace this y. You've seen this y. We get this y there. We replace it. Let's replace it. We are replacing it here. Okay. And if we did so, we are going to have c to the power 4, c to the power 4, okay, divided by x to the power 2, dx. And if we integrated this, of course, we can write it as, we can factor out the c also outside there, factor out the c to the power 4, integral from a to b, and then write x as x to the power minus 2 dx. Okay, if we factored out this, it becomes c to the power 4 divided by 2, and then this becomes equal to, what does it become equal to? It becomes equal to x, to the power negative 1, because we're adding a 1 divided by negative 1, and then we have the integration constant from a to b. All right, then eventually, just 1 minute, trying to create some space. Okay, drawing a boundary. Okay, there we go. Then therefore, our c to the power 4 divided by 2 integral of x to the power minus 1 divided by 1 from a to b. This gives us c squared over 2. It gives us a b to the power minus b. This is minus, right? A minus b to the power minus 1, then minus becomes a plus, a power minus 1, and yeah, which can also be written as equal to just c to the power 4 divided by 2, and then we have minus 1 over b, 1 over b plus 1 over b plus 1 over a. Okay, so the final solution therefore, and this, if you wanted to, we can factor out the minus outside, so it becomes minus c4 divided by 2, then we'll have 1 over b, then minus 1 over a, something like this. I think this looks better. All right, now let's work out the final solution. Our y bar is equal to minus c to the power 4 divided by 2, 1 divided by b, minus 1 divided by a, and then divided by the total area, which we said is equal to c squared ln natural log of b minus natural log of a. And then if we do the division, part of this cancels out, will remain only c squared there. So this finally becomes equal to minus c to the power 2, okay, c to the power 2 divided by 2, and then we have this expression of 1, we have this expression of 1 over b minus 1 over a divided by ln b minus ln a. Okay, so this is our final solution, right? This is our final solution. I think this is about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue subscribing. Bye bye, and see you in my next screencast.